Now we're going to talk more about the nucleus and how it works, and then what kinds of decay are going to happen. So then we're going to start talking about when a nucleus decays, what happens. All right, so I'm sure you've heard it before, but it bears repeating. Nucleons are protons and neutrons. They're basically, a nucleon is whatever makes up the nucleus, right? So we know something like electrons are not something that makes up the nucleus because they're floating around the nucleus. So nucleons are the particles that make up the nucleus, which is protons and neutrons. Okay? Now, of course, the protons determine the structure of the electron orbits, and the neutrons are there as kind of this cement, because if you think about it, these protons are all super close together. They don't want to be close together. Like, that is defying all rules of physics as we know it. So neutrons do kind of act as that cement, but it still doesn't really help it stick together. It's not just the neutrons that are keeping it together. So what's keeping a nucleus together? Something called the strong force is keeping the nucleus together, which, if you can believe it, is the strongest fundamental force of the universe, is the strong force. The strong force has to be so strong that it overcomes that electric repulsion that two protons have. Like, two protons do not want to be beside each other. Okay, so there are 4 fundamental forces, and the strong force is the strongest of the 4 fundamental forces. So I think it's very aptly named. But really important about this, it only acts over a short distance. So think of it kind of like Velcro. So just like when you have Velcro, if it's like close enough together, then it sticks really, really, really well. But as soon as you bring it just that enough bit apart, then it basically doesn't work at all. Okay, so it's only if it's like super, super close, and then if it's super close, it really, really works. But as soon as you bring it far enough apart that there's no things touching, well, in the example of Velcro, there's no more fibers touching each other, then there's zero force whatsoever. But with Velcro, as long as it's within enough of a short enough distance that those fibers are touching each other, it's going to be together, and it's going to be together very, very well. So that's kind of what I liken it to. The strong force is kind of like Velcro. So because of the strong force, you couple that with the neutrons in the nucleus, it does stay together. Okay, so then we still need to use this neutrons as kind of this glue that keeps it together. So the strong force isn't quite enough. So the strong force plus the neutrons work together to keep those protons together. And so that means the more protons you have, the more neutrons you need to have. But at a certain point, the nucleus doesn't really want to stay together, okay? So that's where decay comes from. When we just have too many protons in a nucleus, that nucleus still does want to start ripping itself apart. So 83 is the number. Usually when we go over 83 protons in the nucleus, that starts to become an unstable nucleus, and it wants to basically rip itself apart because there's just too many protons. Doesn't matter how many neutrons you add, it's just not stable. It doesn't want to stay like that. So that's the stuff that will decay and be radioactive very, very easily, is elements that have more than 83 protons in the nucleus. So of course have an atomic number greater than 83. Okay, so before we go on to that, I just want to talk about isotopes. I know you've all heard of them before, but again, just a reminder. So atoms with the same number of protons but different number of neutrons is an isotope, right? Usually a nucleus will have the same number of protons and neutrons, but in this situation, if it has a different number of neutrons, then it is an isotope of that thing, right? So for example, carbon-12, well, carbon, I'll tell you right now, well, carbon has a atomic number of 6, right? So that means it has 6 protons. So if it's carbon-12, the 12 is just telling us how many nucleons there are. So that means that there's 6 protons and 6 neutrons. So that's kind of the most stable and the most common form of carbon. But you can have an isotope of carbon that's carbon-14, and that means that you have 6 protons still, because you always have to have 6 protons if it's carbon, but it means you have 14 nucleons, meaning you have 6 protons and 8 neutrons here. Whereas with carbon-12, you had 6 protons and 6 neutrons, and that's not the isotope, that's just kind of the regular thing, and then of course carbon-14 is the isotope. Okay, so plenty of elements have this, but there's a few more that are just more abundant. Some other examples is hydrogen. Hydrogen 1 basically is just H11, meaning it has 1 proton and no neutrons. But we can have heavier forms of hydrogen. We can have hydrogen 2, which is called deuterium, which has 1 proton and 1 neutron. So we write it like this, where we have 1 at the bottom, that's how many protons you have, and 2 up here, meaning that's how many nucleons, so that would be 1 proton and 1 neutron. And of course, an even heavier form of hydrogen is hydrogen 3, or tritium, which is written like this, meaning we have 1 proton and then 3 nucleons, which means the other 2 are neutrons, of course. Okay, so I'm sure you've written elements in this kind of form many, many times, so this is really just a refresher for you. But all elements do have isotopes. But remember, atomic mass on the periodic table is an average based on the natural abundance in the environment. So, for example, for carbon, there's a lot more carbon-12 out there than there is carbon-14. So they take the mass of carbon-12 and they're like, well, 90% of the stuff on the universe is carbon-12, so we're going to average that out and multiply that by 0.9. They take the mass of carbon-14, they're like, okay, well, the rest of the 10% is that, and so we multiply that by 1.1, and then they add them together. Okay, so we're not actually going to be using the atomic mass on the periodic table very often, because we want the masses of the specific isotopes. Okay, so those are great for just general, but we don't really use the masses on the periodic table. Because when it comes to calculating for radioactive decay and things like that, we need very, very specific masses. Okay, and then of course all isotopes above atomic number 83 are radioactive, because when you have more than 83 protons together, it just cannot be stable. Okay, also another thing that you've probably encountered before is an atomic mass unit. Okay, that's what AMU is, but just a refresher, this is what 1 atomic mass unit is, just because sometimes it's so difficult to measure in these, times 10 to the negative 27, 26, 25 kilograms. So 1 atomic mass unit is 1.6605 times 10 to the negative 27 kilograms. So remember that. Okay. All right, let's move on. So let's actually talk about radioactivity, because that's what we're here to talk about. So what is radioactivity and what's it caused by? Well, it's caused by the disintegration or decay of an unstable nucleus. So remember, that's a nucleus with more than 83 protons. So it can happen naturally. So if there's just an unstable isotope in nature, it can just naturally radioactively decay. But then we have artificial radioactivity, and that's just when it's an unstable isotope and it's produced in a lab by a nuclear reaction. So again, a lot of the elements on the periodic table that are above 82, I can't remember what it is, but it's above a certain number, they're all just synthetic, right? They're not actual elements that we find in nature. They've all just been made in a lab, and then they can't stay that way. They can't stay as an element because it's just, they're too radioactive, they're too volatile. So during radioactive decay, there's possible of 3 types of rays that can be emitted, okay? So we were able to figure this out by just putting the rays in a magnetic field or something like that, because what happens is some of them bend and some of them don't, and the two that bend in opposite directions. So here we have the alpha decay bending here, so that it's alpha like that, and then we have beta decay over here, and then we have our gamma decay right here. So those are 3 different types of decay that we're going to be going over. But again, depending on how they bent in the magnetic field or in the electric field, so same thing in the electric field, alpha decay bends less than beta decay, and gamma just goes straight through. So hopefully you can already kind of see possibly the nature of some of these decays. So here we can tell that alpha and beta must have some sort of charge, but gamma doesn't because it just goes straight through. Okay? So if an element that undergoes radioactive decay is changed into another element, that's called transmutation. Okay, because the mass number and the atomic number change. So that basically is this element going to give off some protons, and that we of course know the number of protons in the nucleus determines the structure of the material. So if it gives off some protons there, that means you have a brand new element, right? So if we have one element changing into another element, that is called transmutation. So that's really important to note. Okay? And then we have the parent nucleus is the original, and the daughter nucleus is, of course, the product. Okay? So what has to happen in radioactive decay? Well, there are certain physics principles that, of course, just have to be followed, that have to happen, and that is conservation of charge, because charge cannot be created or destroyed. So the total charge on each side of the equation has to be equal. So the charge before the decay should equal to the charge after, of, say, if there's 2 daughter products or something like that, okay? Another thing is conservation of nucleons. Okay, so you can't create or destroy those. You need to have the same amount of nucleons, i.e. things making up the nucleus, on both sides of the equation. Okay? So those 2 things really need to happen in a radioactive decay kind of situation. And that'll make more sense when we go over those equations. So let's go over the actual types of decay that we have. First, we're going to go over alpha decay. So the symbol is an alpha. I know it looks kind of weird here, so I just draw it like that, okay? And so, what is an alpha particle? You've heard about it many, many times. Now I'm finally telling you. It's helium. That's what an alpha particle is. It's just helium. So that means that you have this nucleus that's radioactive. It lets off an alpha particle, and then it's left with however many protons and neutrons, okay? So the alpha particle has 2 protons and 2 neutrons, so it's that specific isotope of helium, which isn't an isotope at all because it's helium at its most stable form. So it lets off a helium atom, and then of course we're left with however many protons and neutrons on the other side, right? So here we have uranium that has an atomic number of 92, and then 2 of those protons are going into the alpha particle. So of course we have atomic number of 90. We had 238 nucleons. We lost 4 of those nucleons, so of course it's now 234. Okay, that's all alpha decay is. It's just letting off a helium particle. So alpha decay isn't, when you hear about radioactive decay, all of a sudden you're like, oh no, this is going to be bad. No, not all types of decay are that bad. Like this one has very low penetrating ability, so it's going to be stopped by your skin. So if it happens to something around you, you're going to be fine, okay? Whatever stops it, it absorbs all its energy, they come to a stop, it's fine. But if helium is inhaled or ingested, it can cause internal damage because it has really high ionizing ability. It can strip atoms of their electrons. You don't want that happening in your body because it can be cause some damage. Now, I know you're freaking out because you're like, but what about all those people who like suck on a helium balloon or whatever? Obviously, if you do it once or twice, it's not going to hurt you, but there's a reason why there's like dangers and there's warnings around that to not inhale too much helium, because it will be bad for you over amount of time if you do it too much. And the reason it's bad for you, again, is just because it does have that ionizing potential where it can take an electron from something in your body, and then it can create two ions, and you don't want two ions going around your body. Your body really needs to be balanced, okay? It really doesn't want to have different number of electrons, because as we know, something without a full energy level in your atom can be very volatile, right? So you don't want something without a full outer energy level in your body. So that's why when it's ingested or inhaled, probably not as good for you. But here's a funny thing that happens. There's a reduction in mass between the parent and the products that results in an increase in the kinetic energy. So let's go over that again. The mass reduces, but the energy increases. So why is that? So for example, here I have a radium atom right here, okay? Say it's not moving, but it's going to undergo radioactive decay. So it has a certain mass before, and then after decay, one of the daughter products is going to go that way, and one of them is going to go that way. So sure, that gives us conservation of momentum, but it doesn't give us conservation of energy. And that's because some of the mass from the original atom is going to be converted into energy, because we know that, remember, Einstein has that mass energy equivalence, and we are going to be talking about that more in a future lesson. But note that is going on between during radioactivity, is that sometimes you're losing mass to energy, right? You're creating energy by losing mass. And so that's another thing to look at, is that the mass here is not going to equal to the mass down here. Okay, and we're going to go into that in more detail later. All right, so let's just write a few of these chemical equations of different isotopes undergoing alpha decay. Okay, so we have uranium-238. So that means there's 238 nucleons. I need the atomic number of uranium. It's right down here. So here it says it has 92 protons, okay? So uranium, so it has 92 protons and 238 nucleons, okay? So that just means it has 92 protons, and then if we do 238 minus 92, that gives you the number of neutrons that it has. But we don't actually need that so much right now. So we know it's undergoing alpha decay, meaning it's going to let off a helium particle or an alpha particle, okay? So we know that's what our alpha particle looks like. It's helium with 4 nucleons and 2 protons. Now remember, we need conservation of charge, so we should have the same amount of protons on each side. So that means, since this was uranium-92, we're taking away 2 of those protons. So I need to know what element has an atomic number of 90, because of course we have 90 protons. So then we go here and look at that, it's thorium right here. Okay, so now we're going to have thorium, which has 90 protons. We also need conservation of nucleons. So here we had 238 on this left side, so we need 238 on the right side, but here's going to have to add up to it. So 238 minus 4 is 234, right? So there we go. On each side, 90 plus 2 is equal to 92. 234 plus 4 is 238. So we have our conservation of our nucleons and our conservation of charge happening. Okay, so let's do one more. Alpha decay of, what's PO again? alpha decay of polonium, 210. So if we look for polonium, it's right here on our periodic table. That is element 84, meaning it has 84 protons. And of course, we have the isotope 210, meaning it has 210 nucleons, meaning if you added the protons and the neutrons together, there'd be 210 of them. Okay, again, alpha decay, so we're letting off a helium atom. Just so you know, it can be written like this or like this with the actual alpha symbol. I don't care which one you write. It's completely fine to write that HE. I just want you to be aware, so if you ever see the alpha symbol with the 4 and the 2, you know, oh, right, that's helium, okay? So you can write it either way. I'm not fussed whatsoever. You just need to be able to recognize both of them. Okay, so again, we need conservation of charge. So we have 84 protons right here. So I need 84 protons altogether on the right side. So I lost 2 of the protons. So 84, so I need the one with 82 protons. So it's going down to lead, which is really good because lead is one of the most stable elements. Okay, and then of course we need conservation of nucleons. So I have 210 on the left side, so I need 210 on the right side. So that means I have 206 here because 4 plus 206 is 210. There we go. That is how we write alpha decay. Just remember to have that conservation of charge and that conservation of nucleons. But not too difficult, hey? Not too bad. Okay, the next type of decay we're going to go over is beta decay. So there are 2 types of beta decay. The symbol is this, it's a beta. Okay, it's kind of like a uppercase B, but with a little tail on it. What is a beta particle? It's an electron. That's all it is. Okay, a beta particle is an electron. So this is basically something just giving off an electron. And you're going, but wait, what does that have to do with the nucleus? I'm getting to that, I promise. So beta decay, again, it's not that one that you need to be super afraid of when you hear about radioactive decay. It does have lower ionizing potential, but it does have a bit higher penetrating ability than an alpha particle. But it's stopped by something like a thin piece of wood. Okay, so it does go further through the air than an alpha particle, but it loses an energy when it collides with an atomic electron. But again, as long as it doesn't have enough energy to make that electron completely go out of its all its energy levels, you're going to be completely fine, right? So let's talk about what beta negative is, because again, just letting off an electron is not radioactive decay because nothing's happening to the nucleus. So that's not actually what's happening. It's not just letting off an electron, because that just happens all the time. So what's happening is a neutron is turning itself into a proton. Yeah, you heard me. A neutron is turning itself into a proton when beta negative decay happens. So this is when something wants to have one more proton, wants to go up, okay? But again, we need conservation of charge. This can't just randomly happen without keeping conservation of charge. So a neutron turns itself into a proton, so it has one more positive charge than it did before. So guess what? We need a beta particle. We need a negative charge in order to balance that charge. So you get one extra positive charge, but one extra negative charge means charges are balanced out in the end. Okay? And nucleons are also balanced because neutron, proton, they're both nucleons, so it doesn't matter. And that's what beta decay is. It's when a neutron turns itself into a proton. It also makes this thing called an antineutrino, okay? And you don't need to know much about an antineutrino. It's basically, they didn't discover it at first, and then they were just looking at this whole thing but without the antineutrino, and they realized there was no conservation of momentum, which is a big problem. And then they discovered this extra tiny little particle and they called it an antineutrino, and it did kind of go off here. And then once they brought that into the calculation, they're like, yay, there's conservation of momentum. So it's just something that does go, it doesn't have any charge, but it's just really tiny, really small, really light. Okay, so that's what beta negative is. So the electron isn't like buried within the neutron. It's really just produced during an interaction, okay? And no, we're not going to go into that interaction in physics 30. That's a little bit beyond us. And so again, that antineutrino pretty much has no mass, no charge, so you do not need to worry about it, okay? And then there's a thing called a beta positive decay. So again, beta negative means electron is given off. Beta positive is when a positron is given off. What's a positron? It's the antimatter of an electron. It has all the same characteristics of an electron, except for it's a positive charge. So it's exactly the same as an electron, but with a positive charge. And so that's why it doesn't really stay in our atmosphere very, very long when there's a positron decay, because it'll collide with an electron and then it'll annihilate, and we're going to go over that later in the unit. Okay, so this is when a nucleus has too few neutrons for stability. It needs another neutron, so it takes a proton and turns itself into a neutron. And then, of course, we still need that conservation of charge, so then we have a positron ejected from the nucleus. Okay, so this is when we have a proton turning itself into a neutron. So here we had positive charge, and then here we don't have a charge, so of course we need an extra positive charge somewhere to keep that conservation of charge going on. And then this one has a neutrino, okay? So how do you remember which one has neutrino and antineutrino? The way I remember, there always has to be one piece of antimatter. So here the positron is the antimatter. Right? It's just like the matter we have, except for it's just the opposite charge. And then with beta negative, the antineutrino is the antimatter. Okay? So beta particle, you're like, oh, that's just an electron. So antineutrino, because we need a piece of antimatter. But when it's positron decay, then the positron is the antimatter, so the neutrino isn't the antineutrino, it's just the regular neutrino. Okay? So that's that. So here, if we had something with an atomic number of 91, and then one of those protons turned itself into a neutron, then we're going to have one less proton, okay? And then, of course, it's going to go through that transmutation there, and it's letting off a beta positive particle, so we still have a total charge of 91 on both sides. So let's go over a few of these examples. And we have to figure out if it's going to be beta positive or beta negative. Okay, so if it just says beta decay, then you're just going to assume that that's beta negative, okay? It will say specifically if it's positron decay, as you see down here. Okay, so we have beta decay of radium 226. So if we go to our periodic table, we got to look for radium, which is, I do know where it is. Where is it? It's right there. Okay, atomic number 88. So radium, atomic number 88. And of course it's isotope 226. That's how many nucleons we have. So when we have beta negative decay, what do we know? We know that beta particles being given off with a -1 charge. Now, for the nucleons, remember, we put a 0 here because an electron is not a nucleon. Only protons and neutrons are nucleons. So we need to put a 0 there, and it is really important because, of course, we want conservation of charge. Okay, so since the left-hand side has a charge of 88, so does the right-hand side. So since this says negative, this one now has to be 89 protons. So what has 89 protons? This guy, actinium. Okay, so that's AC, I believe. Yeah, AC. And that will now have 89 protons, and we still have 226 nucleons here since the beta particle is not a nucleon. Okay, and then for the neutrino, we draw this little symbol. It's like a weird kind of bent V. And for the antimatter, we put a little line over it to say that that is an antineutrino. And if it's not an antineutrino, we leave the line out. Okay, so there we go. That is beta decay of radium. I would suggest pausing right now and trying beta decay of thorium here, 230. And then you can turn it back on when you're ready. Okay, yeah, I'm gonna go over this one. If you already did it and didn't have a lot of trouble, then just skip ahead to make sure you get the right answer. So thorium has atomic number of 90. It's right there. Okay. And of course, nucleons is 230. It's undergoing beta decay, so that is beta negative. We just assume it's beta negative if it just says beta decay. So it is gaining a proton here. So what is it going to? It's going over here to proactinium. Okay, because we need 91 protons now to balance out the negative charge. So it's 230 nucleons. And then, of course, since it's beta decay, we need a piece of antimatter. And there we go. There's our antineutrino. Finally, let's just do one example of positron decay. So we have cesium 144. What is cesium's atomic number again? Where is it? It's right there. Okay, so cesium right there, 55. Okay, so we have 55, and of course, it's isotope 144, so that's how many nucleons I have. And now it's undergoing positron decay. So we just write that beta there, but we do +1 there and a 0 there. Okay? Oh, by the way, I forgot to say in this last one, you don't always have to use beta, just like alpha. There's two ways to write it, so you can just write an electron there. Unless it's a positron, then you do need to use the beta. But just so you know, we can see a lot of different things here. Okay, so let's go back to positron decay. So we have that positron being given off, but of course we need conservation of charge. So now, since the left side's 55, the right side also has to be 55. So the new element will be atomic number 54. Okay, and what did that go down to? That went down to xenon, which we know noble gases are super duper stable, so we can see why cesium might decay into xenon because it's then nice and stable. Okay, so it decays to there, and we have 54, and we still have 144 nucleons. And then remember, this is now, since we already have our bit of antimatter, then our then our neutrino is not going to be the antineutrino, it's just going to be the regular neutrino. Okay, and there we go. That's how we write the things for beta decay. The final type of decay we're going to go over is gamma decay. So it has this symbol. By the way, that's how I kind of write it. It's just weird. It's like just a weird loopy thing, okay? And you kind of just try to go for it. Some people do like a little tail on it. Ooh, that was gross. Don't do that. But some people do something like that. I say don't get that, worried about it. So there you go. There's a gamma. What's that? That's just a photon. So that's what's happening in gamma decay. Now, gamma decay, this is the one. You hear radioactive decay, this is the kind of radioactive decay that you want to be worried about, right? And you're saying, what are you talking about? Photons aren't bad. Yes, they are. Just think about what kind of photons are bad. Remember, when you get higher than visible light, higher frequency, that's when photons start to become destructive. And so with gamma decay, we're talking about like X-rays and gamma ray photons. That's why it's gamma decay, because it's letting off gamma rays. And we already figured out gamma radiation is real bad, right? So that's what this is. It's letting off gamma rays, which we know is not good. So it's a really high frequency, really high energy. So it has some very destructive abilities. Okay, so what happens? How do we know that gamma decay is happening? Well, this is created if a nucleus collides violently with another particle. So you have to like really smash them together. And then the nucleus moves to an excited state from ground level, which, yes, nucleuses have excited states, which I know you just thought the electrons did, but nucleuses do as well. And so then this nucleus is in this excited state, and then when it drops back down, then it lets off this gamma ray photon. Okay, so there's no actual transmutation happening here. Okay, it's just a nucleus going from an excited state to its ground level state, and it lets off a gamma ray, and it's just real bad. okay? Because it has the most penetrating ability. You guys know what gamma rays do, or gamma photons do. They are not very, very good. So a gamma ray will penetrate like several centimeters of lead, several meters of concrete. Doesn't ionize, but it just has a ton of energy. Okay, so that's what gamma radiation is. So let's just go over what that situation looks like, because there's no transmutation. So say we have Pu is, I think, plutonium. Where is it? Yeah, it's right there. It's plutonium 94. Okay. So again, this isn't going to go into anything else. So how do we write this with something that's not actually going through any transmutation? What we do is we put a little star here. That's all we do to say that this is in an excited state, okay? That's all that star means. And then, of course, it leaves its excited state, so it gives off a gamma ray. So we just draw that gamma right there. And then it just becomes plutonium in its normal state. So we draw the same equation, we just don't put a little star by it, okay? So that's all you got to do. So they're the easiest equations to write, because not a lot is happening as far as transmutation. Okay, so here's just another quick breakdown. So remember, alpha decay doesn't have much penetrating ability. It will be stopped by a piece of paper. Beta will still go through the piece of paper, but then be stopped by your skin or something like that, or at least, go just a little bit in the hand. But the gamma will it'll go through everything, okay? And that's the one that you got to be really, really worried about, because if gamma radiation goes into your skin, your bones, it can start to mess with your cells and mutate your cells, and that's really, really, really bad. So here's just a table with a quick breakdown of all the 3 types of radiation. So just make sure you know these things about alpha, beta, and gamma radiation, okay? So really quickly, just wanted to go over the different types, the different effects of different types of radiation and their nuclear isotopes, okay? So you've probably heard of something called radiation sickness. And that is when your cellular material has been ionized, and this does disrupt your biochemistry. It can kill cells. It can be really, really bad. Okay? Blood cells and intestine lining are especially susceptible. So this is why we do not want to inhale or ingest anything that's really, really ionizing for us, because it's going to be really bad. It will lead to nausea, vomiting, diarrhea, headache, inflammation, bleeding, all that fun stuff. Okay, so that is radiation sickness from something that's ionized, something in your body. Of course, genetic damage is when we have those higher energy particles, those gamma rays. They actually alter DNA, and this is why it leads to cancer and mutations. And that is why gamma radiation is so bad for us, because that's what's happening when something is radioactive. That's the kind of the thing we think about of radioactive. Remember, alpha and beta decay are also radioactive, but they're not the ones we have to worry about as much. It's that gamma decay, when we have something that has a lot of protons and it's an excited state and then is knocked back down to its ground state. It just gives off these gamma rays, and they're very, very bad. Okay? So something like plutonium. Plutonium is just a very naturally radioactive substance because it's just not stable. So if you even breathe in a microgram, remember that's times 10 to the negative 6 grams. So that little bit of plutonium dust, you will likely have lung cancer in 30 years. Like, it will stay in your body and it will just continue to mutate your cells, right? Until it creates cancer. So that's just a teensy little bit. So that's why when we talk about radioactive decay, if there's any of this gamma radiation that's happening, it's why it's so important to, as people, just get away from that situation as quick as possible. And then we can't go back there and clean anything up. We do not want to risk any chance of having to live with that kind of radioactive decay. Okay? Then you have something like strontium 90. This is similar to things like calcium. It is absorbed by bones, but that's not a good thing. Like calcium, when it's absorbed by bones, is good. Strontium being absorbed by bones really absorb it quickly, but it's bad because it damages bone marrow. Okay, so if this is again something that has radioactive decay, it's not good. Will reduce red blood cell production, can cause bone cancer, leukemia. So again, not a good thing. So the lesson you should take from this is, don't ingest a lot of alpha or beta decay, please. Not good. Ionizing potential. And if there's any chance of anything having gamma radiation, get out of there. Like now. Okay? All right, you guys, that is it for now. I'm going to keep going tomorrow. I know this is a long one today. So thanks for sticking around. Thanks for listening, and I'll talk to you later.